Hello, let's make Tetris.
So just before we get started with the coding video, I just want to show you what we will be building. And as we can see, we've got a Tetris shape here, and it's standard Tetris. We can rotate the pieces, there's collision detection based on the pieces, and if I'm successful enough to make a line with these random pieces, in the short time I have to make this video, there we go, perfect. We see we get a line and all the pieces drop down and the score improves as necessary, and we can drop down lots of pieces until we get a game over, and we can see the pieces don't overlap, the collision is all working fine. Great, good. Oh, game over, only 500 points.
Now before you all go, ugh, what was that? Right? That was Tetris written using the command prompt. And if you're here to learn how to program computer games, let me tell you to remember that beauty is only skin deep. Sure, it's important that games look nice. It is in this day and age. People really like that. It appeals to people and it does sell titles. However, all of the fun, all of the gameplay, the logic, the rules, the challenge is implemented in what's called the game engine, and that sits beneath the graphics. And if you want to learn how to program games, that's where you're going to need to start. You can always get the artists to worry about the graphics later on, and you can even take your game engine and typically slap a different graphics engine on top of it. We'll do graphics engines in a future video, but for now I want to focus on the game loop, the collision detection, the scoring mechanism, user input, and all the stuff that there isn't a huge deal of resources available online. Lots of people doing videos about graphics, not many people doing videos about engines.
The first thing a game needs is some assets. That's the stuff that the game will use as part of its playing. So in this case it's going to be the Tetromino blocks. That's the posh word for the shapes used in Tetris. And I'm going to store those as a string. So we're going to store those as a W string actually. And there are 7 of them. So let's construct the assets. Because I want this to be a bit of a tutorial video, I am going to deliberately inflate some of the code just to make it easier to understand why I've made the decisions that I've made. So in this case you'll see me constructing the shapes as strings, and this is just to keep everything nice and visual for you. So my Tetromino is going to be a 4x4 array of, well, yes or no, and we'll see what that means in a minute. So 4x4, you can see it's going to be 4 elements wide by 4 lines deep. And let's create our first Tetromino as being the 4-piece vertical, the one used to actually create a Tetris. And so I'm using a full stop symbol to represent empty space and a capital X to represent part of the shape. And by appending them in this way, what we end up is creating a single string, but we can visually see what the shape should be. So let's create the other shapes. There we've got the 7 common shapes used in a game of Tetris.
One of the things you'll see me doing a lot of today is not using multi-dimensional arrays to represent these 2D shapes and concepts. Instead I'm going to be using single-dimensional arrays and changing the index as required using, well, simple mathematics. Let's have a look at what I mean by this.
Let's take this square as a 2-dimensional array. You would typically index it as being 1, 2 and 3 in the X axis and 1, 2 and 3 in the Y axis. And you'd have some notation that looks like this: A, X, Y. That's all well and good, but I'm not going to be using that today because we can do some tricks with the indexing to help us out a bit. For example, we've just seen that we've created a Tetris block using this kind of notation. What we don't want to do is create blocks for every possible variant of this. So don't forget, in Tetris you can rotate the shape. So an equally valid rotated shape would be this, and so forth. I'm not going to draw them all out. But I don't want to create an asset for every single shape. So we're going to change how we index this array to facilitate this rotation for us. When we allocate this array in memory, what actually happens is we get a contiguous block of memory addresses like this. 15, there we go, very nice. And if we wanted to say, let me just choose a different colour just to highlight it, let's say we wanted element 10 here, what we can actually say is the index I is equal to the number of rows down, which in this case would be our y value, so it would be 2, times the width of the array plus our x position. Let me just put some numbers to this. So in this case our y index is 2 and our x index is also 2 and the width of the array is 4. So if we calculate this, 2 times 4 plus 2 equals, perfect, 10. So we can take our x and y coordinates and calculate where it exists in our single dimensional array. I'm going to be using this a lot. Consider the situation where I want to rotate the Tetris piece. In this case, we'll have a rotation of 90 degrees. If we take our indexes, we can see that actually our 0 goes here, and we count down in this way now. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. We can make an equation now that represents the rotation at 90 degrees. And what we can see here is if our x and y is 0, then actually the index we want is 12. So it's probably a good bet to start with the 12. And we can see that for an increase in y, we just see that y is added to 12 in this case. So when y is 1, it becomes 13. So we'll add our y. And when we analyse our x here, what we see is that it decreases by 4 depending on x. So 12 take 1 4 is 8, and so forth. And that's true for all of these rows. So in that case, we'll take our x and multiply it by 4. There we go. So for 90 degrees, we've got an equation which can basically rotate our single two-dimensional array, but give us the indexes appropriate for a 90-degree rotation. And I'm not going to draw them all out, but it goes without saying that you can also do the reflections. So 180 degrees here is the equivalent of y times 4, take x, and 270 degrees gives us 3 plus y x times 4. If you don't believe me, go and draw them out. So we only need the one asset now, and we can index it in a way where we can emulate a rotation for the Tetris piece. We'll be using this a lot. Now I'm just going to paste in a little function. I've already typed it. I'm not going to make you sit and watch me type everything for this video. I want to keep it reasonably quick. And so this is the rotation function that takes an x and a y for the piece, in this case px and py. So that's our original index here. So this is the x and y coordinates. And it also takes in a value r, which is 0, 1, 2 or 3 for 90, 180, 270 and 0 degrees, and it returns the appropriate index given the equations we've just worked out. Now we have some assets and a way to access them that gives us the rotation. We also need another asset now, which is the playing field itself. The playing field is going to be defined by two variables, field width and field height, and that's 12 and 18, which I was counting the cells on a version of Tetris from the Game Boy. That seems to be correct. And we're going to store the elements of our field as an array of unsigned chars. Now you'll see I've not statically allocated this, it's going to be allocated dynamically. And the reason I'm using unsigned chars is I want 0 to represent empty space, and I want 1 to represent part of the shape, 2 to represent a different shape, and so forth, including the boundary wall. So all of our map information is stored within the one array. And this bit of code is going to initialize the array for the playing field, so we can see here the unsigned char array, field width and field height, and I just want to set everything in that array to 0 unless it is on the side of the array or at the bottom. So I have a condition here. You'll see this is the same notation we were using before, where we're using y and x but using it in a sequential manner. And so if the x boundary is 0, or it is the width of the playing field, or it is the height of the playing field, then I want to set that to 9, and I'm going to be using the value 9 to represent the border. Otherwise, set it to 0, empty space. Now, it's about this time we probably want to start drawing some stuff just to make sure things work. Now, if you've seen my first-person shooter at the command line, or you've seen my Game Boy emulator at the command line, you'll know that I'm quite fond of the function which allows us to just use the command line as a screen buffer, effectively. And I'm going to do exactly the same here, no different at all. In fact, I'm just cutting and pasting the code from that project right now. So we've got a screen width and a screen height variable to use, and I've set those to be the defaults that would normally be included with a Windows command prompt, so 80 and 30 in this case. will have seen this code before. I'll just zoom out a little bit so we can see a bit more of it. It creates an array of wchars, in this case, for the screen width and screen height that we've just seen, and it fills it full of blank stuff, and it grabs a handle to the console buffer and sets it as the active screen buffer. So instead of cout doing anything now, we have to use a separate command to draw to the buffer. Write console output character draws our screen array and the dimensions starting at position 0, 0 to the console. And before we can draw anything, it's at this time we want to start thinking about our game loops.
Game loops are the most important part of your game engine. These are the things that sequence everything that's going on. Now, a simple game like Tetris is not going to be some massively event-driven application. It will typically include some elements that will handle timing, user input, updating the game logic, and then drawing it to the screen. And it just keeps doing this until the game is finished or the user exits.
Here I have implemented a very simple game loop. We have a flag game over. If it's not game over, it just sits updating the output with what can be seen. So in this case it's just our screen buffer array. Nothing that interesting. So we actually want to draw in our playing field. Okay, let me talk you through this. So the field represents the whole board. So this is the boundaries, the empty space, and the Tetris pieces as well. We again just iterate through X and Y, and this time I'm offsetting them by 2 because I don't want to draw it right in the top left hand corner of the screen. It looks a bit pretty and shows you that there is a boundary there. But then I've got a little interesting fiddle going on here, which is where I am basically setting the output depending on the characters in this string array. So let's look at the index here. So if in our field array the value is 0, we will draw what's this position in the string here, which is empty space. 1, 2, 3, 4, 5, 6 and 7 represent the Tetris pieces. In this case I'm just using the letters A, B, C, D, E, F and G. Equals is going to be for number 8. That will be when we make a line. We'll see that a bit later on. And I'm going to use the hash symbol to represent the border. And we just use the array. Again, you see this very familiar layout now for the equation y equals width plus x. We'll take whatever position is in our field array, and that will give us a number, and we'll use that number to index into this string array to decide what we display on the screen. It's quite an elegant way to do this and avoids us having unnecessarily complicated switch statements and compound if statements. So let's try this and see what it looks like, just to make sure everything's working. Perfect, we can see a Tetris boundary here.
Because I don't want this video to be half an hour long, I'm not going to go into great detail explaining every line of code, but the code is available from the links below. It'll be available on GitHub and the onelearncoder.com blog. Please take it, hack it and do what you want with it.
A simple game engine main game loop will consist of the following parts. The first thing we'll want to worry about is timing. Now, you might have seen from some of my other videos, timing is important because people's computers aren't the same, and some will do things faster than others, but we want a consistent playing experience for the player. So we'll always handle timing. Then we'll want to handle some user input. I'm not going to be using event-based user input for this. The old games consoles didn't use event input really, so we won't use it here. And when we're going to need something that represents the game logic, and this is where we'll do the shapes falling, the collision detection and the scoring. And finally we want to display the output. We'll call it render output. And you will find these 4 stages in almost every computer game ever. Tetris is all about stacking blocks, so collision detection is really the most fundamental part of this game engine. And the nice thing about Tetris is it's actually quite a simple collision detection engine, because Tetris shapes always move one square at a time. This means we'll never have a situation where we're looking for very small overlaps of squares. We're not building a physics engine here. Everything will move one whole cell at a time, and this means we can do a very simple collision detection engine. So I'm going to use blue here to represent the overall field array, which will consist mostly of zeros. I'm not going to draw them all in. Oh, why not? I'll draw them all in. So everywhere where there's empty space in our field is represented by a 0. But let's assume we've got some other pieces in here. So let's take one of these L-shaped pieces. I'll label this as a 2 so it stands out. So maybe 2 is represented. You can see the overall outline of the L-shaped piece there. I'll shade that in. And we've got some more zeros. And maybe, I don't know, we've got some other piece here. For Tetris collision detection, before we move the piece, we want to make sure that we can fit it in that location. And to do this, we iterate across all of the cells in our Tetromino array using our rotation that we calculated before, and we make sure that all of our cells contain a full stop in this case, and if it's a full stop and a zero, that's fine, it's empty space and empty space, and we want to make sure that anything that represents solid bricks, in this case an X, is also on empty space. So in this case we've got an X with a zero, so that's good. And we've got an X with a zero, X with a zero, X with a zero. Good, this piece fits in this location. Therefore, any movement to this location is valid and should be allowed. Now consider the scenario where we've got the same piece, but we've also got some additional pieces here. So I'm going to put in the ID 4, and I'll just cautiously draw those in. There we go. What we see now is we still get lots of valid hits, but now we're also checking an X with something that's not a zero in the background. So this is a fail. The piece cannot fit here. So we can't rotate it to fit here, we can't slide it to fit here. It's not valid and therefore gets rejected. And because we're going to be doing this a lot, I'm going to create a function specifically for it. Does piece fit? And we're going to take the ID of a Tetromino. We need to know what the current rotation for that piece is. So we know what function, what parameter to pass into our rotation function, and we need to know the location of the piece in the array. In this case, it's the top left cell of the Tetromino, which is represented by pos x and pos y. By default, what we'll do is always return true. And this is nice because if anything causes it to fail, we'll just immediately return false. There's no point in checking lots of locations. If any of them fail, the first one it encounters, then the whole thing doesn't fit. I need to iterate across the Tetromino, so I'm going to have a simple nested for loop here, each going from 0 to 4. And just to be explicit about this, I'm going to get the index using our rotation function. So this is the index into the array of the Tetromino. And I also need to use a similar piece of code, but without the rotation, to get the index into the field based on where the current playing position is. So remember, the pos y and pos x is the top left of our piece, and py and px is the index in. So that way we've translated our 4x4 Tetromino array into the field array. And we'll be seeing this, as I said before, we'll be seeing this all the time, this y times width plus x. Now, because we're programming in C, we need to be careful that we're not going out of bounds when we're doing these array checks, because we'll be accessing memory which isn't ours. The collision detection is a single one-liner, really. We take our Tetris piece, which will be one of these, specified as an argument to the function. We've worked out our rotated index, so we know that we're checking the right index. So if the Tetris piece's index is equal to an x, and the playing field is not equal to 0, then there must be a collision. There's something already in that playing field, so we return false. The piece cannot fit there. So straight away, fail.
Before we jump straight into writing the game, let's just quickly test that some of our routines are working. It's always good to double check these things.
There's not very much that represents the game state in Tetris. You just need to know what current piece is falling, is it rotated, and to what angle, and where is it located within the field. And in this case, because it's the first piece I'm going to fit in, it's going to be set to the field width divided by 2. So it's somewhere near the middle and at the top of the playing field. Whereas the playing field contains all of the information to be rendered, the currently active piece, the piece that's falling and under control by the player, needs to be drawn separately because it's not part of the field yet. And to do that, we iterate over all of the cells of our Tetromino. So the current piece there, so it's the current Tetromino that's falling. And we want to get the index, which is rotated. So quite nicely here, we go from our 0s to 4s in the x and y's and use the current rotation to give us the correct index. If that is equal to an x, then we want to draw something to the screen. Otherwise, it's empty space. It's the part of the Tetromino which we don't care about. And I'm just drawing this by using again our y times width plus x. Told you you'll see this a lot. And I'm offsetting it by the current position of the piece. Plus our 2, because remember our playing field is also offset by 2. So that's the same for y and x, but this time the screen width isn't the field width, it's the width of the entire console buffer. And I'm setting that to, rather oddly here, the current piece plus 65. Well, what's going on here? I'm taking the ID of the current piece and adding 65 to it. If we look at our array up here, of the Tetromino pieces, we'll see that, for example, I want the 4 piece, the straight line piece, is at index 0 in our Tetromino array. So in this case I've got 0 plus 65, which in ASCII is the letter A. So I'm taking our Tetris piece and adding it to 65 to give us A, B, C, D and E in a way that mimics when the playing field is drawn. Also it displays the pieces as A, B, C, D, E, F and G. So let's just double check that that's actually running. Good, we can see that the Tetromino is not falling anywhere, we've not implemented that yet, but it's drawing it with the appropriate characters. And just to double check, if I change the current piece to, say, piece number 1, perfect.
To test our collision, we're going to have to get some user input sorted, which also means we have to think about the user timing.
Fortunately, because this is Tetris, timing is very simple. Things happen on a common tick. There is no continuous or fluid movement in Tetris. As we know, everything moves cell by cell, and everything is allowed to move at the speed the game is currently playing. So I'm just going to emulate that by hacking in a simple delay here of, let's say, 50 milliseconds. So that's one game tick. And if you've watched any of my other command line videos, you'll see what I'm going to do here for the input is use something called get async key state. And we're going to need a little bit of extra logic up here, just to store the current keys. Now I'm only going to bother with 4 keys for my game, so that'll be the left arrow, the right arrow, the down arrow, and I'm going to use the Z key to rotate the piece. And the way this works is it goes through the array of the 4 booleans representing the state of the keys, and it uses the get async key state function, which tells me is that key pressed or not. If it is pressed, this returns a true. And I'm using this constant string expression again here to check this out, and these are the virtual key codes required. So this X27 is the hexadecimal for the right key, the left key, the down key, and the Z key, and it goes through all 4 of those, just checks which are true and which are false. So I end up with an array here of true or false. It's nice that, isn't it? All just in sort of one line of code. So let's see what happens when the user presses the left key. So in this case, if B key 1. The user has pressed the left key, so the first thing we'll need to do is check, does the piece actually fit to the left of where it currently is? So we'll use our doesPieceFit function. DoesPieceFit, and it's the current piece, the current rotation, and it's not the current X, it almost is, but we want to check to the left, so that'll be -1. Current X, -1. And the current Y is unaffected by moving the piece left or right. So if the piece fits, then we can say n current X equals n current X -1. So the piece fits, this is a valid move, let's update our current X variable. We'll do exactly the same for our right key, but in this time, instead of checking to the left, we want to check to the right, and update accordingly. So let's see if that works. Holding down the right key, yeah, it doesn't go out of bounds. I'm holding down the left key and it doesn't go out of bounds. Very nice. And of course, we can do exactly the same for moving the piece downwards. But in this time, instead of checking for horizontal motion, we want to check for vertical motion. And in computing, top left is always 0, 0. Let's just try that as well. So left and right, and down. Whoomph. Perfect.
Even though this is a tutorial video and I'm trying to do things as simply as possible to explain the point, I'm a C++ programmer. I can't resist trying to optimize this bit of code.
When you see nested ifs like this, you can probably always just replace them with a logic AND instead. And because the result of this if statement is so simple, we're just choosing whether to add 1 to a number or not. We can do that in line as well. So n current X is added with either a 1 or a 0, depending on the result of this condition. So we'll just throw in a condition statement there and output a 1 or a 0 appropriately. And get rid of that now. And we'll do exactly the same for our other keys too.
Totally unnecessary, but looks quite cool.
I've just added exactly the same type of code, but to handle the rotation this time when the user presses the Z key. So our rotation gets incremented, and it tests to see, well, does the next increment along, is that valid? Can we fit the piece there or not? And if it's true, then permit the increment. Let's try this and see what happens. So I can move the piece around, I press the rotation button, and oh, it looks good. And you can see the collision detection is now working even though we've rotated the piece. Actually rotating once is proving quite tricky, so we need to make the rotate latchable, and that's because every 50 milliseconds it's trying to force a rotate if I've got the key held down, so we want to put a lock in there. We're going to need a flag which suggests whether the user is holding down the rotate button or not. In this case we'll just set this to false, and using a little bit of code down here, if the key is pressed and they're not already pressing it, then we go ahead with the test. Only in that situation, so if they are holding down the key already, the test will fail and it will increment rotation by 0, i.e. not rotate at all. We also now want to say that we are already holding the key because B key 3 was equal to true, so we set that to true. And if we're not holding the key, then we set it to false. And if we just quickly test that, that means yep, I'm holding down the key, you can probably hear me smashing it there. It only rotates 90 degrees at a time, regardless of how long I hold down the key for.
When playing Tetris, the piece is forced down periodically, every few tenths of a second. So we'll do the same.
To begin with, we want the pieces to fall slowly. So we'll take the game tick here, and let's say we want the piece to fall down every 1 second. We want to accumulate 20 game ticks in this case. As the game progresses though, we want it to speed up, so we'll then want to do perhaps just 19 game ticks, 18, 17, all the way until it's unplayably fast. Let's add some counters then. So we've got our speed, which is basically the current level, the difficulty of the game. And we're going to have a counter which is counting game ticks, and when the number of game ticks equals the speed, we want to force the piece down. So for every game tick we increment a speed counter there, and if our speed counter equals our current speed, we want to force the piece down, otherwise we don't, so we can do that as a single one-line Boolean expression there. The guts of this will go into our logic. We've already handled the player movement, but now we need to handle basically the game, so when it forces the piece down. So if B
Tetris is quite simple, that it will keep forcing a piece down until it can't. And when it can't, that means it's done, it's locked into place. And that's when we'll take on the next piece.
So as the piece is forced down, if on this particular game tick it is, the first thing we need to do is, well, does it fit any further down? So we can use our doesPieceFit function, and if it can, do it and carry on. Nothing interesting is happening, it can do it. However, if it can't fit, then we've got a whole sequence of things that we need to do. Firstly, we'll need to lock the current piece into the field. So we're accumulating tetrominos now. The current piece gets put basically into the background. It becomes part of the furniture. It's an obstacle for the player. Once we've locked the piece in, we want to check, have we created any full horizontal lines? If we have got some lines, we'll probably want to do something with them. We'll come back to that, but then the final stage is to choose the next piece. But if we can't fit the next piece in, it's game over, and we can do that one straight away. Our game over flag will just finish our while loop if the piece simply doesn't fit. Choosing the next piece is very simple. We just want to set it back to its starting position, set the rotation to 0, and we just choose one of our pieces at random. Of course, this is only pseudo-random. Locking the current piece into the field is very simple. We just take our Tetromino 2D array and translate it into the field in its current position and rotation. So we go through it element by element. We take that from the Tetromino array. If there is an X there, then we update our field with the current value plus 1, because 0 in this case is empty space, but 0 also represents one of the shapes in our Tetromino array. I guess we could have created a shape which was no shape at all, but hey. And let's not forget to set our speed counter back to 0 again. Let's see what happens now. So every second the piece seems to be falling on its own, that's good. The collision detection is all well and good, rotation is working, and I'll press the down button and force the piece into place. And great, it's found the next piece. And that's because when it tried to force it down itself, it couldn't do it. So it said, right, well, I've got to lock that piece in place now and find another one, create another one at random. And we've got very basic Tetris up and running here. But what we'll notice is we have no line detection. So it's a game of Tetris you can only lose, I'm afraid. You get no points and all you do is fill it up.
If in Tetris you created a line and it just instantly disappeared, you probably wouldn't feel very rewarding. So we want to reward the player by some visual cue that something has happened, they've formed a line. In this case I'm going to change the horizontal line to a load of equal symbols.
Checking for lines is actually quite simple. Firstly though, to be optimal, I don't need to check the whole playing field. I only need to check where the last Tetromino piece existed. So those 4 rows that the piece occupied, they're the only 4 I need to check for lines. I cannot have created lines outside the boundary of the Tetromino. So my loop here takes the 4 rows of the Tetromino and translates them into the field space. So it's the current position of the piece plus the offset of the Tetromino, and I'm just putting in a quick boundary check to make sure that we're not checking stuff beyond the boundary of the array. Now, I've started by assuming that there is going to be a line, and the way I want this to work is if there are any empty spaces in the line, this gets set to false, so it can't be a line. And I'm checking everywhere in the playing field for 1 row, except for the first and last cells, because they're going to be boundaries. I don't want to include those in the check. And if any of these elements, so here you'll see my y times width plus x again to index the field two-dimensionally, if any of those get set to 0, then this becomes false. If we get to this point in the code and b-line is still true, then it must be a line. So we're going to set all of those elements to be number 8, which represents the equal symbol when we draw it out onto the screen. I just wanted to set up a little test here just to make sure. So, oh, there we go. Yeah, it turned into an equals, but we've not got rid of the line yet, so we're only halfway there. Because I want this little visual indication of lines to disappear at a later point in time, I'm going to have to store the fact that some lines exist. So I'm going to use a little vector for this. So if the line exists, simply push back the current row. Now this works quite nicely because we can use the vector empty function to say have we got some lines and behave differently if we have. So if we have got some lines, the first thing we want to do is we're going to update our display buffer. We're going to cheat a little bit here. We're doing a bit of game logic in the drawing loop, and this is not an uncommon practice in game engines. And what we want to do is just basically delay. We want to show the player the equal symbols for approximately half a second or so. And then we want to remove the lines, but then also move down all of the pieces above the lines. And this is simply done by iterating through the vector. So if a line exists, we've got a number for the line, which comes back. That gives us the row. And then we want to iterate column by column across the row, simply moving the pieces down. So in this case, we update the current field position, again with y times width plus x. Going to hammer this point home with the position above it. And the top row is set with zeros, empty space. And we clear our lines out then. Let's see how well that works. So here I've got a line which is not the bottom line or the top one. And we'll see if it disappears when this piece falls into place. Turns to equals and disappears. And you get that sort of nice pleasing clunk. Excellent.
We've almost got a fully working game of Tetris now. Let's add some scoring and increase the difficulty as time progresses. And then I think we're done.
To increase the difficulty, we're going to need to keep track of how many pieces we've currently delivered to the player. And we're going to, let's make an assumption that every 10 pieces we want to increase the speed, make the game more difficult. We'll just add a little bit of code in here when we're locking the piece in. We increase the count, and if the count is a multiple of 10, we want to decrease our speed. Remember, speed is the count of number of game ticks, so as this gets smaller, the game gets faster. And if we want to keep score, of course, we're going to need a variable called score. We'll have two approaches to scoring. One is simply every piece you get 25 additional points. But the other one, to encourage the player to take risks, we want to score the lines. And if the player gets one line, we give them 100 points. But if they get 4 lines, we'll give them 1600 points. So there's an exponential thrust there in order to keep the player trying to go for bigger line removals in one go.
It's little tricks like this that make games addictive. If we always awarded the same score for the number of lines, players would only ever go for one line at a time. But by rewarding them more, we get them to take bigger risks.
And the final touches to the game is one will display the score. In this case, we'll display it slightly to the right. I'm just using the printf string function here to display the score. And of course, if they game over, they might want to see what their score was. In which case, I'm going to just go right down here. Remember, this loop will exit on the event of a game over. And we'll put that in. So, oh dear, they've had a game over. First of all, we'll do some tidying up of our console because we can't really use cout whilst we've got hold of the screen buffer. And we'll display a game over message and the score. Let's put it all together. Let's just see what happens. There we go. We can see our score. So for each piece, we get 25 points. That's good. Started off well here, haven't I? I'm going to do good to get a line straight away. And so here we're going to get a line. Excellent, so they got a big score for getting a line.
And there you have it, Tetris in, well, about 200 lines of code. I hope you've enjoyed this video. If you have, please give me a big thumbs up and perhaps subscribe and share it. As I said before, the code is available in the links below or the onelearncoder.com blog. Keep on coding, have fun, I'll see you next time.